Okay, this is a message to Kyle. This is my first attempt, man. I will make this as quick as possible, but I do apologize if it gets lengthy because I'm just trying to show people something that I don't think people realize about just constants, the idea of constants in math and physics as related to geometry, because geometry is rigid. The relationships that come out of that geometry are just helpful to be aware of in the math, and this is just the okay. I'm going to explain this best I can. I'm going to point to these areas here without messing up my picture. So I drew the circle. Okay, so just start at the beginning, because this is two ideas merged into one, and that's why I kind of got excited about this, is because this first circle, the smallest circle, there's two circles. There's a small one and there's a big one. The smallest circle simply has a radius of 1. But what I've done here is that 1 is now a triangle, so that all sides of every triangle is 1. But the smallest triangle. So the way I kind of look at that is there's a triangular grid, an equilateral grid of ones. But because all sides are 1, you can just understand the units of each triangle, small triangle, as 1. So, okay, let's just go up here. That's 1 unit. The area of that is 1 unit. Then we go, there's 3 units right here. 1, 2, 3. Just those 3. Okay, 1 is an odd number, and 3 is an odd number, and 1 plus 3 is 4. Right? Okay, 1 plus 3 is 4. I think we're good. So what I've done here is this. When I say C equals 4, I'm talking about these 4 triangles. And those 4 triangles have a side, the C length of which is 2. It starts here, there's 1, and here's 2. So side 2, 2 squared equals 4. C squared equals 4. Alright, so this is A, and A squared, it's just a unit triangle. So that's 1. Now, when we, okay, this line right here, the square root of 3, it's also this line. Okay, so when you do the square root of 3, you have a 90-degree triangle with this 1 and this 2. 1, 2, square roots of 3. This is a cosine law on 60 degrees when you do the math and the identities and the fractions. So, okay, here's my question. There's this 1, where's a good spot to show that? That's the best spot. This is 1. This is 2. This is the square root of 3. This diagonal, it's 2 diagonals. So when you look at the math behind an equilateral triangle, the height of the triangle is square root of 3 over 2. If this is 0.5. Yeah, so if this short line is 0.5, if all sides are 1, then the height of this is square root of 3 over 2. So if the side is 1 and we have 2 of those, we just have the square root of 3. And then according to Pythagorean's theorem, we have a squared, and consider this b squared. Okay, so b, that's this line, same length line, so b squared is 3. Square root of 3 times square root of 3 is 3, so that's cool. It's really neat. But the way I started this many years ago was to start at the center and draw a circle with radius 1, and then draw a circle with radius 2. Within that circle, I draw that triangle. What came out of that was a radius 1 circle, a radius 2 circle, and a triangle with height of 3. And then the diameter of the entire big circle is 4. So just the circle, without anything else going on, the circle alone with this triangle and this triangle represent a 1, 2, 3, 4 relationship. Okay, and so when you do that relationship, the sides of the big triangles here, not just that each side is a square root of 3. square root of 3. So every side is the square root of 3 from here to here. Remembering that we're dealing with the two altitudes of the triangle to know that that's just root 3 everywhere. Okay, so then what I did was I came up with a 9 by 9 or a 3 by 3 grid, which adds to 9. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's also 9 below that. 1, 2, 3, 4, 5, 6, 7, 8, and then 9 here. And you just text messaged me, interesting, as I'm recording this right now on February 2nd, 2021. Okay, so we've got the 3 by 3 grid up here, which adds to 9 units. We've already counted these above this line. Now if I count the same symmetry, do 9 more triangles down here, another 3 by 3 grid, I have that. So then I do 1 is A, the square root of 3 is here, okay, and it connects at this weird angle because it's a different size. It's bigger than this, but it's smaller than that. And I shaded this in 3 different shadings. I don't know if you can see that. There's a dark shading, there's a light shading, and there's no shading at all. Because each part of this is a half triangle. It just flipped. So this is one triangle. The area of that is 1, the same way that this is. It's just, instead of cutting it down the 90 degree, instead of the faces coming down this here, the faces are coming together here, making a different shape, but it still represents 1. So 1, 2, 3. So if 1 plus 3 equals 4, you have a squared plus b squared equals c squared. And it's fucking beautiful. And what's not here is the golden ratio. But if I put every association on the same drawing, it gets really difficult. So I'm sitting here thinking, and I mean for a long time, how I can add another relationship without it getting more confusing. So I want to go to another page to simplify that. That's the master sheet. That's like your cheat sheet, okay? But yeah, this is the next step. Or I mean, not the next step, but to simplify how I got here. And I don't know what my fascination is with this process. It's just a meditation. It's something I do for fun. But at the same time, I feel like there's some really important shit happening. So I just started with a dot, and then I started with 3 dots, and then I went on to 6 dots, and I got 1, 2, 3, 4, 5, 6 dots. I mirrored that down here to just get, you know, the same 6 dots. But then I connected the dots, connecting the dots, and we have this equation here. There's 2 Q's here, there's an A and a B, there's 3 Q's down here. There's an asymmetric relationship between the top and the bottom, yet the equation here is the equation. So this is this is what I had on the other sheet, where this is a unit 9 triangle, and this is a unit 9 triangle. 2 and 2 is 4, and 1 is 9. 2, 2 and 2 is 6, plus 3 is 9. I call this my 3, 6, 9 triangle, because Nikola Tesla talked, if you understood the power of 3, 6, and 9. So anybody who's heard that sees this delivered in that way might perk their ears up. So here's the Pythagorean thing, where he just did 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's kind of the same idea. So, and also what's not here, oh, Q, I do have it. Okay, A plus B, or A, B, C, and Q are all equal. Okay, so here's another way of looking at this. Remember, the 2Q is here. But what we're doing, I want to point out, this would be what I would call like the 0 point. The perfect point of equilibrium and balance. What you need to do here is really imagine that this line can extend back and forth, slide back and forth. As that happens, the size of these triangles all change. This one kind of spinny. This one kind of gets bigger. So C will get bigger as this line moves to the left. A will get smaller, and at some point we'll get to when we actually hit this point, B and C will be equal. This Q will fall away. This Q will fall away. This Q will fall away, and this Q will fall away. if I slide this all the way, the animation would be, C would grow and grow and grow and grow until it equaled the same growth rate as B. But anytime you do this, you're getting this scaling factor. That's what's powerful. And I call this the flux capacitor right here. See A angle here makes a Y. The A and the B and the C, that's the flux capacitor Y right here, extended to its furthest conclusion within a grid of relative units. So hopefully by now, and maybe not, because I don't know how, I really can't tell how far people are following what I'm doing. But if I go back to this, we're talking about square numbered areas, okay? So 2 squared is 4. We start up here. 1 squared is 1. 1 squared is 1. But 1 plus 3 is 4. 1 plus 3 plus 5 is 9. That's this 3 by 3 grid. All 9 of these triangles. But if I keep going, I get 16 triangles. So 9 plus 10, 11, 12, 13, 14, 15, 16. Okay, now all I can demonstrate here is 16, but if you keep the triangles going down, you get 25, 36, 49, 64, 81, 100. It's an equilateral pattern that people have not recognized. And I have pages and pages and pages on that. But what I'm teaching today is beyond that. Okay, it's looking at it different. I'm continuing to try to find the simplest, most basic, like trying to remove any obstacle. Because like at a certain point you can do all this crazy stuff here, okay? And this is a good page to look at, but I got to the point where I'm labeling things. Everything's labeled and it just looks like crapola. I like the way it looks to a certain point because it's artistic and I do my doodling and all my shit. I show my thought process, so I can do a whole video on this. We're moving into 15 minutes. I'm going to keep it at 15 minutes, but I just want you to know that I'm still checking and double checking and triple checking. But these ideas aren't even really all mine, okay? What I'm doing is I'm just connecting an idea. This guy named Wayne Roberts, who is the only other person in the land that talks about the triangles being squares. Oh, I like this page. This is a pretty one. That's a pretty one. So, yeah, there's like the idea of a linear versus the relative analysis. So here's my flux capacitor. Okay. 1 square root of 3, 2. The trick here is that, the trick here is that this square root of 3 is really this line. So I've just dropped it to make it look balanced and not just like a triangle on a page. It's like a dangling mechanism, like here's gravity and this is a string hanging, and you know, you can do all sorts of cool stuff with this is what I'm saying. Like the utility on this is extended to the square numbers in physics. But we're not talking about squares. We're talking about triangular unit areas, and it's different analysis. Okay, it's like a different kind of way of thinking about it. And I've got the math locked, and I'm trying to develop a lesson plan. And here's what I sent you. Dot matrix. The reason I call this the dot matrix is because I just started with dots. Okay? But again, these aren't really my ideas. I just am connecting it. Oh, here's a good one. This is just one triangle, but it actually has the square root 3 triangle drawn on top of the c squared triangle with 4 units. So if I draw all the lines here, I have 4 triangles inside of this right here. 1, and then 2, 3, 4. I've got 1 here, and then I have a triangle that's root 3 because it's this diagonal all the way across 3 times, and the area of this triangle is root 3 squared, which is 3. So 1 squared plus root 3 squared equals 4, which is 2 squared equals 4. So here's in the simplest terms. I can't get any simpler than that. I hope you enjoy my presentation. It's 14 minutes and 37 seconds later, and I really have not even started. I'm just doing the best I can to get it in there quick. I know you're a busy guy. I might upload this video just go ahead and upload it to YouTube and give you a private link. Keep it unlisted until you either give me the approval or whatever. But anyways, 15 minutes on the dot. See ya.